Okay, hello again. So we've done a common source amplifier, and the other two are common gate and common drain. Let's look at a common gate amplifier now. I'm going to start with the resistive load. Again, this can be replaced with an active load, right, where the resistor would then be an active device, such as a PMOS device for the case that I'm going to work on here. So drawing a common gate amplifier. So first, let's think about what does common gate mean? Well, if I have a device, in common means AC ground or AC common node, not necessarily DC ground. So in this case, my gate must be an AC ground, but I will have to apply a DC bias because it's an NMOS device here, and I need to keep this device in saturation. If I didn't apply a bias at the gate, my device would be in cutoff. I would have 0 volts VGS. In a common gate configuration, the input is always applied to the source. So I'm going to apply a VN here. Now, I may also apply a bias to the source if in certain circuit topologies, but in this case, I'm going to do a simplistic form and just ground my source on the bottom side of my small signal VN. And on the common gate amplifier, the output is taken at the drain node of the device. And again, I'm going to have a resistive load, so I'm going to apply my load RL, and RL will go to VDD. So here's my basic configuration of the common gate amplifier with resistive load. So now I have to do what? First, I have to bias the device such that's in saturation. So the first thing you do is bias the device for saturation or check that the device is in saturation. Remember, amplifier devices, MOSFETs, must be in saturation to work properly and to be able to do a small signal analysis. So now I'm going to draw the small signal model of just my MOSFET at low frequency. We're doing low frequency analysis. So I have VGS, I have GM VGS, I have my R0 of my device. All right, my drain node, my source node, my gate node. Again, let's start with the gate side now, and we can start plugging this into the circuit. The gate of the device is V bias in schematic, which is AC ground. Let's check. Does that make sense? Yes, because this is a common gate, meaning the gate should be AC ground. My source is where my input signal goes, and this is a small signal input, so it remains in small signal model as VN going to the source. And my drain is where I take my output, so I can call that V out. And it is also where I have a load resistor going to VDD in the schematic, which will be AC ground and small signal. So I have a load resistor going to ground. So again, to analyze this circuit for voltage gain, I need to apply KCL and KVL, set nodal equations, and solve. So I'm trying to solve V out over VN, or small signal gain of the common gate amplifier. So at my output node, I'm going to write my KCL equation first. So at V out, I have V out over RL as the current going through the load resistor RL. I have, for the current going through R0, I have V out minus V in over R0, because V in is at the source. And then I have my plus GM VGS, voltage controlled current source, and now all currents going out of the node equal to 0. So here I have one equation with V out, V in, and VGS. So I need to find a way to remove VGS. If I go over to the gate side, you can see that VGS is VG, which is 0 volt, minus VS, where VS is actually V in. So I can say VGS, as my second equation, is equal to VG minus VS, which is 0 volts minus V in. So VGS is equal to minus V in. Let's get rid of that. Okay. So plugging this VGS equation into the first equation, I will have V out over RL plus V out minus V in over R0 plus GM times minus V in equals 0. I can collect terms, move V in to the right side, and divide. So doing all of that, I will have V out times 1 over RL plus 1 over R0 equals GM plus 1 over R naught times V in. So V out over V in, which is the small signal gain, is equal to GM plus 1 over R naught divided by 1 over RL plus 1 over R naught. Now let's take a look at this equation. The 1 over RL plus 1 over R naught in the denominator, that is a parallel combination of resistors. If I make the assumption, which is a very good assumption to make, that 1 over R naught is much, much smaller than GM, I can pretty much neglect R naught, 1 over R naught. And we know that's true because R naught tends to be very large, right? So 1 over R naught should be very small. So if I do this, I have the small signal gain of the common gate amplifier is approximately GM times RL in parallel with R naught. What does that look like? That looks very similar to the gain of the common source amplifier with the resistive load RL. So if we compare the two, if I have common gate and common source, I would have the voltage gain to be minus GM RL in parallel with R naught. Common gates, I have voltage gain to be approximately GM R naught in parallel with RL. So very similar gain magnitude. The difference is in the sign. A common source amplifier has a negative sign. This does not mean that it attenuates the signal. That wouldn't be good, right? V in would be larger than V out in that case. This means phase inversion, right? Or inversion referring to phase shift of 180 degrees between the input and output. So the output is 180 degrees out of phase from the input. So if you go back and think about your Bode plots, when you do magnitude and phase Bode plots, the magnitude of the gain between the common source and common gate amplifiers is the same. It's just that the common source is 180 degrees out of phase, output to input, and the common gate is not. So we call a common gate amplifier a non-inverting amplifier because the output and the input are in phase with each other. A common source amplifier is called an inverting amplifier because the output and the input are 180 degrees out of phase. Okay, so I hope this gives you, again, more exposure to analyzing a different circuit, the common gate, and then sort of highlights for you that the gains are very similar between the two, the voltage gains, just one is non-inverting and one is inverting.